So before we do the next example question in chapter 15, in the text, there is a section on the formula that allows us to convert between values for Kp and Kc, one way or the other. This formula is not given to us on the exam, and I won't ask you to derive it as such, but it's important that you are able to do so. So let's just show that quickly, and then we'll do a couple of examples. And let's give ourselves an equation to work with that's rather straightforward, but interesting enough to show how this formula works. And let's do this all in the gas phase. So if I were to write the Kp expression for this reaction, this was equal to partial pressure of C squared over Pa squared times Pb. Now, each of these gases is behaving ideally so that for each of them, Pb is equal to nRT. And therefore, the partial pressure is actually equal to a concentration term, because that's what number of moles per volume is, times a constant RT. This product is also a constant because that's the gas constant, and the reaction occurs at a constant temperature. And so normally we write N over V as a square bracket term. And so I'm going to make the following substitution in my expression. So instead of writing pressure, I will write concentration, and that was squared, times RT. And I square that too. So sometimes this is a little part here that we forget to do when we're doing this ourselves. Concentration of A squared, RT squared, concentration of B, times RT. So if we look closely, we can see that inside the expression for Kp, there's actually a Kc term. So let's pull that out and recognize that it is in fact equal to Kc, which would be C squared over A squared times B, and then factor out the RT term. And the way I gather the exponents is the power here would be equal to 2 minus 2 minus 1. And so in this particular case, Kp is equal to Kc times RT raised to the minus 1, or in other words, Kp is equal to Kc divided by RT. So that's not the formula that works for all equations. This is the way that these two terms are related for this particular equation. So what is the general formula? The general formula for Kp in terms of Kc is equal to this times RT raised to the power of the change in the number of moles of gas molecules. And so delta N for this reaction is products minus reactants, but only for the gaseous term. So if there was a solid in this reaction, I would not count it. And so I see that it's equal to 2 minus 1 minus 2, and that's why it was minus 1. So think about when these two are actually the same. They would be the same if the change in the number of moles of gas was equal to 0, because this raised to the 0 would be 1, and I would be left with these two being equal to each other. So these types of questions tend to show up on short answer type questions on the exam that illustrate these different conditions. And we can see also, just enough room to squeeze it in here, if I isolate for Kc, Kc would be equal to Kp divided by RT raised to the N. And another way of writing that would be Kp times RT raised to the minus value of delta N for gases. in the equation. So they're really very, very close to each other in terms of expression, so you don't want to get them confused. Maybe you just need to remember one and then obviously be able to isolate, in this case, Kc from that one expression. I think you can use one formula regardless of which way you're being asked. So we'll continue on with the examples from 15.3, I think, but we'll stop here.